Hello, everyone. And we start our concluding lecture by discussing the central limit theorem, which is the most important result of probability and statistics. So first of all, this result is given as theorem 443 on page 216 of the textbook. Okay, so this is theorem 443 on page 216, and it's discussed in section 441 on pages 215 to 220. This result is about normal approximation for rather wide sequences of properly centered and normalized or standardized sequences of random variables, namely given the sequence x1, x2, xn of independent and identically distributed random variables with finite variance sigma squared. So sigma squared should be positive and less than infinity. And automatically it implies that Ax, which we denote by mu, is also finite. So under this condition, the sequence of standardized variables Zn, which is root of n times x bar minus mu over sigma, converges in distribution to the standard normal variable capital Z. So it's also n01. And in practice, Zn is often treated as standard normal for n as large as 25. Some like 25, some like 30 or 50. Although the value of n required for a sufficiently accurate approximation really depends on the distribution. So, and I want to say a few words along those lines. So, and to explain how accurate normal approximation can be, I want to go back to its history. So, De Moivre, Laplace theorem, which was derived, I think, like special case was derived by De Moivre in 1799, about the very end of 18th century. So this was the symmetric case P equal to 1/2, and then Laplace considered a general case of probability of success P in unit interval in the early 19th century. They considered the sampling proportion, which we already denoted by p hat, which depends on n, of course, which is the number of ones over total number of tosses in a sequence of identical and identically distributed and independent tosses of a fair coin. So 1 is interpreted as the head, 0 is interpreted as the failure. So we discussed this model before. And p hat is really the same as the sample mean. Yeah, so you can put subscript Pn because xi is either 1 with probability p or 0 with probability q equal to 1 minus p. So p is between 0 and 1 and it's fixed. Then expectation of p hat is p. That's what we obtained from Bernoulli weak law of large numbers. So, and p hat approaches p in probability as n goes to infinity. But I also want to say that variance of the sampling proportion p hat equals the true probability of success p times 1 minus p over n. So this can be shown with little effort because this is the binomial random variable. So p hat in our case is BNP divided by n, and hence finding the variance of p hat is straightforward in this case. So it will be p times 1 minus p over n. And then what de Moivre Laplace theorem states is that p hat minus p divided by root of p times 1 minus p over n converges in distribution to the standard normal variable z as n goes to infinity. So historically, this was the first CLT type result obtained more than 2 centuries ago. So, and that's how normal distribution was discovered by these two Frenchmen. Of course, you might read about both the scholars. The other discoverer of this distribution was a German mathematician, Carl Friedrich Gauss, whose name I already mentioned in this course. And accuracy of normal approximation here is that the difference is inversely proportional to what actually happens is that the difference will be inversely proportional to root of n times root of p times 1 minus p. I don't give the exact bounds. So what actually happens is that, say it's like constant. Yeah? So the more observations you get, the more accurate this approximation is. But also when p is close to 0 or p is close to 1, this approximation blows up because you divide by 0. So when you divide by something close to 0, then you get a high number. Why? Because for p equal to 0, we really need to use the Poisson law of small numbers discussed at the end of the previous lecture. And if p is close to 1, you simply flip successes and failures. So you just count the number of failures, calling them successes, and you still can switch to Poisson law of small numbers, but not for the number of successes, but rather for the number of failures. And if p is close to 1/2, then there's a special case of a fair coin considered by Abraham de Moivre as where the accuracy of approximation is the best. So in this case, you don't need that many tosses, but when p is close to 0 or p is close to 1, you may still use this normal approximation, but in order to compensate for dividing by a number close to 0, you would have to employ very large sample sizes. Like there is a trade-off between n and p here. So, and in general, the accuracy of approximation in the general case here is inversely proportional to the root of the number of observations. So this 1 over the root of n is actually present here. Yeah, so in the general case. So, but such results actually are true in general case where you have the rate of convergence inversely proportional to 1 over the root of n. They need an assumption on the existence of the third moment. Yeah, so this can be weakened, but we would get into too many particular special cases. I studied that and I worked on this stuff, but this is, of course, outside the scope of this course. So if you're interested, you, of course, can contact me for further references. So accuracy of approximation is always important. And if you use normal approximation, it's important to know that it is not always justified. You ought to justify your conclusions. And I also should say that if your distribution is normal, then you don't really care about how many trials you have. So in case your distribution is normal, Zn will be normal, because what Zn is going to be, just let's take a look. If x1, x2, xn, they're all normal, with mean mu and variance sigma squared, then Zn is root of 1 times x bar minus mu over sigma. But you can write it as x bar minus mu divided by sigma over the root of n, which is x bar minus ex bar divided by the root of the variance of x bar. And x bar is normal. So if you sample from a normal population, then the sample mean is also normal by Cramer's theorem, which we discussed before, and hence Zn is going to be normal 0, 1 for each n greater than or equal to 1. So in the normal case, Zn is normal for any sample sizes, and of course the sequence of standard normals converges to itself because nothing changes. Yeah. And if your distribution of xi's, it's a common distribution of all your observation, is close to normal, then you of course will get a reasonable accuracy of your approximation. But if you have huge deviations from normality for your populations from which you sample, then you can compensate by dealing with very huge sample sizes. Okay. I want to say a bit about what is going on and how we trade off between weak law of large numbers and the CLT. So the resultant normal approximation is the CLT, but it does not mean that X bar converges in distribution to the normal variable, because by law of large numbers, X bar converges to constant mu, which is the mean of the sample mean. So and we have convergence in probability. So if we have convergence in probability to mu, then we also have convergence in distribution to mu. So hence X bar converges in distribution to a degenerate random variable or point mass at mu. CLT deals with standardized X bar. So we standardize X bar, which is X bar that depends on n, and standardized sequence of the sample means does converge to standard normal. Okay? So, and we basically can say that probability that X bar is less than or equal to X is, so we can multiply. So what we can do, we can center by subtracting mean mu here and there, and we can standardize also. We can multiply by root of n and divide by sigma. It's the same as dividing by sigma over the root of n. But this probability can be rewritten as probability that root of n times X bar minus mu over sigma is less than root of n times X minus mu over sigma. And this is probability that Zn, this is approximately Zn. So it's probability that it's less than or equal to root of n times X minus mu over sigma. And this is the value of Laplace, so Gauss function capital phi, at this value of argument, root of n times X minus mu over sigma. And this number can be found from the table for standard normal probabilities. But if our random variable is exactly normal with mean mu and variance sigma squared over n, which is the case for X bar if we sample from normal population. So y is X bar or Xn bar here, yeah? So in this case, we don't have an approximation, so double tilde means that this probability is approximately given by Laplace or Gauss function. But if we deal with normal distribution per se, then our probability that X bar is exactly less than or equal to X is exactly the value of Laplace or Gauss function capital Phi of the argument root of L times x minus mu over sigma. And then this number can be found from the table. Next, I want to proceed with a series of examples on weak law of large numbers, CLT, and various rules that we have discussed today and during the previous lecture 17. So the first question. Xn is an exponential random variable with parameter lambda equal to n, and n goes to infinity. So there are three possibilities, and we need to choose the one which is correct. Yeah? So Xn converges to 0 in probability, Xn converges to 1 in probability, and also that Xn, this sequence Xn, does not converge in probability to a constant. Let's figure out what is going on here. So first of all, mean of the exponential variable is 1 over lambda, so 1 divided by the rate, as you hopefully remember, or it's 1 over n, and clearly it goes to 0 as n goes to infinity. The variance is the square of the mean, so variance of xn is 1 over lambda squared, or 1 over n squared, and clearly it also goes to 0 as n goes to infinity. So, and then we use the variance rule. Expectation converges to constant, variance converges to 0. So our constant C is 0 in our case, but variance goes to 0. Hence, our sequence Xn converges in probability to 0 as n goes to infinity. And therefore, we are to choose the first answer. So the second and third statements are wrong. So please review the variance rule discussed in the previous lecture. And let us discuss the second question. So we have the same sequence Xn of exponential random variables with parameter lambda going to infinity. So lambda equals n, and n goes to infinity. And then we consider a transformed random variable yn, which is 5 times xn plus 2 over xn plus 1. To what target does by n conversion probability? So the hint we are given is that we have convergence in probability. And we are to define where it is going to. Let's do that. So here we need to use the continuous mapping theorem. So we already know that xn goes to 0 in probability, and yn here, which is 5xn plus 2 over xn plus 1, is g of xn, so it's a non-random function of xn, where g of u equals 5u plus 2 divided by u plus 1. But what I want to do now is to simplify function g of u. It's not that hard to show that g of u equals 5 minus 3 over u plus 1. And then we already learned numerous theorems on convergence in probability on top of continuous mapping theorem. So, so 5 is just a constant, and 3 is constant, so we can realize that xn plus 1 converges in probability to 1, because xn goes to 0, 0 plus 1 is 1, yeah? Then 3 over xn plus 1 goes to 3 over 1, because 3 does not change. Xn plus 1 goes to 1, as I already explained. Yeah? Hence, 5 minus, so 3 over 1 is 3, of course, 5 minus 3 over xn plus 1 goes to 5 minus 3, which is 2. And this is an idea of the proof, but in order to make everything rigorous, we have to imply this continuous mapping theory. The next example, question number 3, is about uniform distribution on interval from 0 to n. And again, n goes to infinity. Xn is uniform 0n, and yn is xn over xn plus 1. So we need to show that yn approaches 1 in probability. And we will use a similar trick as before. So the idea will be based on dealing with function g of u, continuous mapping theorem, and so on. But we will also employ the direct arguments. So first of all, yn can be rewritten as xn plus 1 minus 1 over xn plus 1, or 1 minus 1 over xn plus 1. So we, of course, can use function g of u, which is 1 minus 1 over u plus 1, and then employ the continuous mapping theorem. But we also know that we deal with uniform 0n distribution. So, the goal is to show that 1 over xn plus 1, which is, of course, positive, so it goes to 0 in probability as n goes to infinity, which is a kind of making sense, because on the average, xn will be n over 2. Yeah, so we have like n over 2 here, but these variables become huge on the average because the interval is now from 0 to n, and we divide by this number, so 1 divided by a huge number will approach 0, but we need to make everything rigorous. So let's estimate probability that 1 over xn plus 1 is greater than epsilon, where epsilon greater than 0 is fixed. So it's the same as probability. So if you take this guy on the right-hand side, it will be xn plus 1 less than 1 over epsilon, or xn less than 1 over epsilon minus 1. And certainly I want epsilon to be fixed, but sufficiently small. So, but if epsilon is fixed, 1 over epsilon minus 1 is also fixed. And for epsilon less than 1, it's positive. For epsilon less than 1, so we want to deal with small values of epsilon. Therefore, it will be the length of this interval divided by n. So this probability is 1 over epsilon minus 1 divided by n. So the numerator is fixed, denominator goes to infinity, and this ratio goes to 0 as n goes to infinity. Hence, this guy goes to 0 in probability, so I can write that this subtrahend goes to 0 in probability, and hence 1 minus something that goes to 0 in probability. So this whole thing, which is yn, goes to 1 in probability, and that is exactly what I were to prove, that such a sequence constructed starting from uniform 0n distribution converges to 1. Okay. Our next example is as follows. Like we have a generic random variable x, which has finite expected value mu and finite variance sigma squared. So assume that it's positive. Yeah, so we don't want to deal with the degenerate case where everything is the point mass. So then we consider yn, which is this fixed random variable divided by n. And we need to show that it converges to 0 in probability as n approaches infinity. Okay. So in order to do that, we will use the variance rule. So expectation over n is 1 over n times expectation of x, which is mu over n, and clearly this goes to 0. So which is our constant c as n goes to infinity. Variance over n is 1 over n squared times variance of x, which is sigma squared over n, and it also goes to 0 as n goes to infinity. And hence, by variance rule, when n goes to 0, in probability as n goes to infinity. Okay? So that's actually why the variance rule is so useful. Like many results on convergence in probability are just direct corollaries of the variance rule. And instead of proving each such result from scratch, it's much easier to provide a single theorem, which is a sufficient condition for convergence in probability. It's not necessary, but sufficient. And then it's a recipe which is to be used rather frequently. Okay? The next example 4 is of a particular value because it gives us an opportunity to review the Cauchy distribution again. Yeah, so we spent a sufficient amount of time discussing the Cauchy distribution before. It's a kind of counterexample because for this distribution, there is no mean. It's not defined. But let me remind you what the probability density function for this distribution is. Still, I hope that many of you do remember it. And we also have the cumulative distribution function available in the closed form. Okay. So first of all, the PDF f of x is 1 over pi times 1 over 1 plus x squared, where x is between negative and positive infinity. And the CDF capital F of x, which is probability that capital X is less than or equal to little x, where x is Cauchy random variable, is known to be 1/2 plus 1 over pi times the arctangent of Ex, where this is the inverse function to the tangent. Yes, so we discussed how to derive this result before, because the antiderivative of 1 over 1 plus x squared is available in closed form. I also want to remind that if x1, x2, xn are Cauchy distributed, ID random variables, then xn bar, which is such an average of n independent and identically distributed Cauchy variables, is also Cauchy distributed. So this result is a kind of apple tree as the central limit theorem. So Cauchy distributions are stable, and they possess this beautiful reproduction property. So it's a reproductive property of Cauchy distribution. So we keep this in mind, but here we just have a single Cauchy variable, which we divide by n. Okay. So what we need to do is to find probability that our random variable, which is Cauchy over n, is greater than epsilon, which is clearly 1 minus probability that such a random variable y, or it's actually absolute value of this variable y, is less than epsilon. So this is justified by the law of complement, of course, which we considered at the beginning of this course. And therefore, the question on the floor is to find probability that so y is x over n. So we need to find probability that the absolute value of x is less than n times epsilon. Where does it go to? So this is clearly probability that x is between negative n epsilon and positive n epsilon, or f sub x of n epsilon minus f sub x of negative n epsilon. And the CDF f of x is 1/2 plus 1 over pi times arctangent of x. Okay. So therefore, it will be equal to 1/2 plus arctangent of, so it will be plus 1 over pi times arctangent of n epsilon minus the parenthesis 1/2 plus 1 over pi times arctangent of negative n epsilon. And clearly 1/2 here and there cancel out, but arctangent is an odd function, therefore it will be a negative arctangent of positive n epsilon, and we have negative times negative, which becomes positive. And therefore here it's going to be equal to 2 over pi times arctangent of n epsilon, and arctangent of n epsilon as n goes to infinity, it goes to pi over 2. So this guy goes to pi over 2, therefore the whole product goes to 1. So this guy goes to 1, hence this guy goes to 0 as n goes to infinity. So therefore, if you divide a single Cauchy variable by n, it still goes to 0. But we proved it from scratch. So here, the variance rule is not applicable because Cauchy distribution does not have finite expectation. It does not have, therefore, finite variance. But what we are still able to do due to the fact that we have CDF of Cauchy distribution in closed form as 1/2 plus 1 over pi times the arctangent of x. So because of this result, we are able to derive the things from scratch. It's certainly not that easy as using the variance rule, but we cannot employ the variance rule in the situation where the variance is infinite. And the class of distributions considered in question 5 has a special name. It's known as scaled Poisson random variable. So xn is a Poisson random variable with parameter n times lambda. So the Poisson parameter grows. Lambda is positive, of course. So, and therefore, expectation of xn is the same as variance of xn equals n lambda. And then yn is xn over n. We need to answer a few questions. So first of all, for what values of y is probability that yn equals y is positive. And the second question is whether yn converges in probability to a constant. We need to answer yes or no and justify our result. Okay. So first of all, it's not exactly Rykov theorem, it's the converse of Rykov theorem. So we can represent our random variable xn, which is Poisson distributed with parameter n lambda as the nth partial sum of ID Poisson variables with parameters equal to lambda in each case. Yeah. With n ID Poisson variables with parameter lambda. And therefore, our random variable y. So first of all, we answer question B. Yn, it's nothing else but the average of ID Poisson variables divided by n. And by Wick law of large numbers, it converges in probability to expectation of Poisson with parameter lambda, which is lambda. Hence, the answer is lambda. So answering question B is easy because we really obtain that it's a special case of the Bernoulli. Actually, it's not Bernoulli, it's not binomial experiment, but it's an application of the classical Wick law of large numbers for the sample mean approaching the population mean as the sample size going to infinity. So, of course, you may use the variance rule here because variance is finite. Variance of Poisson is also Poisson. But I want to discuss the first question A. For what values of y is our probability that yn equals little y is positive? So probability that yn is equal to y is the same as probability that xn over n is y, or probability that Poisson variable with parameter n lambda is equal to y. So this is positive for y equal to, oh, I'm sorry, so it should be equal to n times y. So we take n from the denominator to the numerator on the right-hand side. So probability that Poisson variable with parameter n lambda, that's what our xn is. So it should be equal to n times y. Yeah. So and n times y should be 0 or 1 or 2, etc. Hence, probability that yn is y is positive is for the values of argument little y equal to 0. So, and y can be 0, then y is also 0, or 1 over n, or 2 over n, or 3 over n, etc. So for Poisson distribution, the support is 0, 1, 2, 3, etc. So here we need to divide by n. And the terminology is as follows. Yn is a scaled Poisson random variable. And I did consider scaled Poisson random variables in my research. The last time I wrote on this was in 2013. So it's an important byproduct of the Poisson family. And say in application, say if you deal with Poisson number of accidents, so you say you can have a flat rate of reimbursement equal to 1 over n, then for the total amount to be reimbursed, it's going to have scaled Poisson distribution. Yeah, and there are some other applications of this result. Okay, so this is important, not as important as the Poisson distribution per se, though. So, question 6. So here we deal with a discrete random variable xn. So xn is such that it's 1 over n for x equal to negative n and positive n, and that's n minus 2 over n for x equal to 0. Yeah, and of course, n goes to infinity. So we need to find the limiting probability. So first of all, we need to check that this is a legitimate probability mass function for each n. 1 over n plus 1 over n is 2 over n. 2 over n plus n minus 2 over n is 1. Hence, the total probability is 1. Our distribution is symmetric because we have most of the mass at 0, and then the weights are 1 over n at negative n and positive n. Therefore, the expectation is clearly 0. So exn is 0 for each n greater than or equal to 2. Yeah. So clearly we need to have n greater than or equal to 2, otherwise this probability is negative, which cannot be the case. Yeah. But what about the variance? So the variance is E of xn squared minus E of xn squared. But since this is 0, we have nothing to subtract, and expectation of the square is 1 over n times negative n squared plus n minus 2 over n times 0 squared plus 1 over n times positive n squared. And this equals 1 over n times 2n squared, or 2n. And 2n goes to infinity as n goes to infinity. Hence, the variance rule is not applicable. So it's a symmetric sequence. So if we have convergence in probability, then our only choice is convergence to the mean, which is 0. But let's see what we can get. So variance rule is not going to work. But variance here is finite, but then it goes to infinity, at infinity. But here it's still possible to show that this random sequence converges to 0 in probability as n goes to infinity. And so we would have to use the brute force method. It's not going to be that hard, though. Okay, because what we need to do is to fix a positive epsilon and estimate probability that the absolute value of xn is greater than epsilon. But let's see what we have. Say epsilon x fixed, but for sufficiently large values of n, we have probability, positive probability at negative and at positive n, and negative and positive n by absolute value will be greater than epsilon. Hence, we will have just the mass 2 over n outside this interval from negative to positive epsilon. So we only have probability equal to 2 over n. Hence, this probability is 2 over n. Clearly, it goes to 0 as n goes to infinity. And hence, our random sequence xn converges to 0 in probability as n goes to infinity. So the variance rule is sufficient, but not necessary. So sometimes when it's not going to work, we are still able to prove convergence in probability. The second, I'm sorry. So our next question 7, actually. So it's slightly more challenging because it uses some results discussed before. But in question 7, we have the sequence x1, x2, xn of independent and identically distributed random variables from exponential distribution with parameter lambda. So therefore, expectation is 1 over lambda and variance is 1 over lambda squared. And then Tn is n divided by the partial sum over I from 1 to n of xi. The goal is to show that such a sequence Tn, which is a random sequence, converges in probability to the rate parameter lambda as n goes to infinity. But when you look at Tn, you realize that Tn is the reciprocal of the sample mean. This is going to help a lot. Okay. So an important observation is that Tn is nothing else but 1 over xn bar. We, of course, will need to use the continuous mapping theorem for the reciprocals, but let's find the distribution of the partial sum of xn. So the nth partial sum sum over I from 1 to n of xi, which is the sum of ID exponential variables with parameter lambda, is known to have gamma distribution with shape parameter n and the same rate lambda. Yeah, so I already mentioned that this is a member of the class of Erlang distributions, which are gamma with integer values of the shape parameter alpha. Yeah, so shape parameter alpha is equal to n, which is an integer number. So for gamma with parameters n and lambda, expectation equals n over lambda and variance equals n divided by lambda squared. So this is also important to remember, but we also conclude that by the weak law of large numbers, xn bar, which is the sum of xi over n, converges to 1 over lambda in probability as n goes to infinity. And then we use the continuous mapping theorem. Use the continuous mapping theorem with our function g of u being equal to 1 over u, so it's a smooth function. And hence, since Tn, I'm sorry, since xn bar converges in probability to lambda, which is our constant c, and lambda is positive, and g of u is continuous at lambda. So this means that function g of u is continuous at point u equal to lambda. So this is the notation used in calculus. Therefore, we automatically obtain that Tn, which happens to be g of xn bar, converges in probability. I'm sorry, so it converges to 1 over lambda. So our constant c is 1 over lambda, but g of u is continuous for u equal to 1 over lambda. So therefore, Tn, which is g of xn bar, converges in probability to g of 1 over lambda, which is 1 divided by 1 over lambda, which is lambda. So the sample mean converges to 1 over lambda. Therefore, the reciprocals of the sample mean converges to lambda per se. Okay? Question 8. So here we have a sequence of continuous random variables capital Xn with the PDFs little f sub xn of little x being n plus 1 over n times x to the power 1 over n for x between 0 and 1, and it is equal to 0 otherwise. It's given to us that our random sequence xn converges in distribution to a certain unknown random variable capital X as n goes to infinity. So we are given that there is such a weak limit capital X, and our goal is to identify the distribution of this limiting random variable capital X using the definition. So first of all, we need to figure out what kind of distribution we are dealing with here. So we are given the PDF. Therefore, let us find the CDF. Let us integrate the PDF. So integrating the power function is straightforward. And therefore, I will simply write down what our CDF is here. So capital F sub xn of little x is 0 to the left of 0. Then it's x to the power 1 plus 1 over n for x between 0 and 1. And finally, it is 1 for x greater than or equal to 1. So let's draw the graph of such CDF. So this is the CDF. Okay, so this CDF is 0 to the left of 0, 1 to the right of 1, and then x to the power 1 plus 1 over n in between. So therefore, it will be something like that. Okay. And let's find its pointwise limit. So fix x. Fix x. Yes, so for x less than or equal to 0, so it will be a limit of zeros. So limit is identical 0. For x greater than or equal to 1, the limit is just identical 1. And we really need to deal with x between 0 and 1. So for x between 0 and 1, so it will be x to the first power times x to the power 1 over n. Which is x times e to the power 1 over n times log x. But log x is just a number. 1 over n goes to 0. Therefore, e to 1 over n times log goes to 1. Therefore, it is actually going to x. And therefore, our weak limit is nothing else but uniform 0-1 distribution. So here we did not consider moment generating functions. We proved that we have convergence to uniform 0-1 distribution starting from the definition. conclusion is that random variable x is distributed according to uniform 0-1 probability law. That's it. Our next example 9. Here we consider the discrete two-point distribution. So for a random variable xn, we have positive probability equal to n minus 1 over 2 times n plus 1 at x equal to 1, and positive probability n plus 3 divided by 2 times n plus 1 at x equal to 0. So we see that for x equal to 0, these probabilities approach 1/2, and for x equal to 1, the probability also approach 1/2, because it will be like n divided by 2n asymptotically. So you get 1/2 for both 1 and 0. Yeah. Therefore, a reasonable guess is that the weak limit should be symmetric Bernoulli random variable, just tossing a fair coin once, and that's it. Still, we need to prove it from scratch. How? So for each n greater than or equal, say, to 2, we want to have positive probabilities at 0 and 1. Hence, in order to have positive probability at 1, n should be greater than 1. So for n greater than or equal to 2, we obtain that Pn of 0, so it converges to 1/2, and Pn of 1 also converges to 1/2 as n going to infinity. Yeah. And if n of 0 is probability that xn is less than or equal to 0, but here the positive probability is only at 0, hence it's probability Pn of 0, and it is n plus 3 over 2 times n plus 1, and this approaches 1/2. Therefore, Fn of 0 goes to 1/2 as n goes to infinity. Fn of 1 is probability that xn is less than or equal to 1, which is Pn of 0 plus Pn of 1, which is 1. So 1 goes to 1, and hence Fn of 1 goes to 1 as n goes to infinity, and therefore for each x greater than or equal to 1, fn of x also goes to 1, because fn of x will also be equal to 1. So really what remains to consider is what happens between 0 and 1. So fix x between 0 and 1. So fn of x is probability that xn is less than or equal to x, but really it's nothing else but Pn of 0, because for xn less than little x between 0 and 1, the only positive probability will be at 0, and this converges to 1/2 as n goes to infinity. Hence, for such x, fn of x converges to 1/2. For each x less than 0, capital F sub n of x is probability that random variable capital Xn is less than x, but this probability is 0 because there is no probability mass to the left of 0. Therefore, if it's 0, so it converges to 0. And therefore, capital F of x, which is the limit as n goes to infinity, of capital F sub n of x is 0 to the left of 0, 1/2 between 0 inclusive and 1 not, and 1 to the right of 1, which is CDF of Bernoulli B 1/2 distribution. It's a single Bernoulli trial with probability 1/2 of success in a single trial. Yes, so that's what we needed to prove. There is a different approach to do this problem, so we can find moment generating function of random variable xn. So it's a Bernoulli trial. Therefore, we can write MGF as Bernoulli MGF, which we know in closed form. And therefore, we can find the limit of such MGF and get that it will be 1/2 plus 1/2 times e to t, which is MGF of symmetric Bernoulli random variable. Okay, but anyway, I discussed how to solve this problem by using the brutal force method. It's also possible to solve this problem analytically by using the techniques of moment generating functions. So question 10. So here we deal with normal random variables. So xn is normally distributed with the same mean mu and variance little n. So they're all centered at mu. So the mean is the same, but variance grows. And the question is whether xn converges in distribution to a random variable. Answer yes or no, and explain how to get it. But we know scaling properties for our normal distribution. How do we get variance n? It can be normal with so it will certain mean, but unit variance multiplied by a constant. So the claim which I want to make is as follows. My random variable xn has the same distribution as normal variable with mean mu over root of n and variance 1 times the root of n. So the mean will be root of n times mu over root of n. Roots of n cancel out. And when we take this root of n inside, so this constant should be squared. So we indeed get the variance equal to n. Yeah. So because of root of n, which goes to infinity, we don't expect to get something decent. But anyway, the MGF, moment generating function, capital M sub xn of t, is the exponent of mean mu times t plus sigma squared times t squared over 2, which is n times t squared over 2. And it converges to positive infinity. So we don't get convergence of moment generating function. So therefore, MGF diverges. So, and then we can use the contradiction argument. So suppose that we get convergence in distribution to a certain random variable. Then moment generating function of the sequence xn should converge to moment generating function of such a limiting random variable. But moment generating function of this sequence diverges. So we don't get anything decent since, so therefore it doesn't seem that we have a certain limiting variable here. So, and the answer is no. The next question concerns the point mass. So in question 11, we consider a degenerate random variable which is concentrated at certain point C. So probability that x equals C is 1. So we need to sketch our CDF at part A of the problem. And then we need to find the moment generating function of such degenerate random variable. Okay. This is our point C. And this is 1. So this is X, this is Y. So there is no mass to the left of C. And we know that for discrete random variables, we have piecewise constant cumulative distribution function, and the jumps occur at those points where we have a positive probability to occur for our discrete variable. So since there is only one value C with a positive probability, which is 1, so we obtain that there is just a single jump equal to 1 at this point C. And hence, our graph is as follows, like from negative infinity to C, it is 0. And at point C, our function makes the jump of magnitude 1 and continues to be at level 1 forever. So this is our CDF. And in part B, we need to find the MGF of such a point mass distribution, capital M of T. So by definition, this is the sum over X of e to Tx times P of X. And we need to deal with those values of X where P of X is positive. But there is just a single value where we have positive mass. It's X equal to C. Therefore, it will be e to Tc times 1. Or we can write it as e to the power C times T. And this is our answer for part B of this question. So this is the graph of the CDF. MGF is just the exponential function with the exponent equal to this value C, where we have the whole probability. So question 12. So our random variable xn is exponential with parameter lambda equal to n. We already considered such sequence before. It seems that this sequence xn converges in distribution to a certain random variable capital X as n goes to infinity. So we need to find this random variable. So in part A, we use the definition. Actually, we will employ the empirical rule. And in part B, we will use the analytical technique of moment generating functions. Okay. So in part A, I would like to remind you that expectation of xn is 1 over lambda or 1 over n, hence it goes to 0. Variance of xn is 1 over lambda squared or 1 over n squared, which is also going to 0. Hence, xn goes to 0 in probability as n going to infinity. Yes, so this is straightforward, but we now need to use the analytical techniques of moment generating functions. So that's what part B of the problem is. So let me remind you that the MGF capital M of exponential variable with rate lambda equal to n, which is lambda over lambda minus t for t less than lambda, and it's infinity for t greater than or equal to lambda. Of course, lambda is equal to n. Yeah. So, but we can rewrite it as 1 divided by. So we can take lambda from numerator to denominator. So we can rewrite it as 1 over 1 minus 1 over n times t. So where t is less than n and infinity for t greater than or equal to n. Yeah. So what would be the limit of this guy? So we take the limit of this guy. T is fixed because we consider point-wise limits. 1 over n goes to 0. Therefore, this converges to 1. So how do we identify 1? But MGF of point mass at 0 is e to ct, where c is 0, which is 0 times t, which is equal to 1 identically. So therefore, this limit 1 is MGF of point mass at 0. Hence, our sequence of moment generating functions for such exponential variables with rate lambda equal to n, with growing value of n, converges to moment generating function of the point mass at 0. Hence, our sequence of exponential variables converges to point mass at 0 just because of the result that enables us to establish the convergence of a sequence of random variables in terms of point-wise convergence of their moment generating functions. And we just have two more questions to consider. Question 13. Let random variable capital S be the sum of 16 independent and identically distributed uniform 0-1 random variables. We need to approximate the probability that this partial sum capital S is greater than 12. And we may use the fact that uniform 0-1 random variable has the expected value 1/2 and the variance 1/12. So, and we are going, of course, to use the central limit theorem. Use CLT also for uniform distribution on interval UB. Expectation is A plus B over 2. Variance is B minus A squared over 12. That's what we started before, and that's what is given in the book. Hence, U01 is 1/2. So expectation of uniform 0-1 is 1/2. Variance of uniform 0-1 is 1/12. And S16 is U1 plus etc. plus U16. So N is 16. That's a decent number, but not too large. Hence, probability that S is greater than 12, which is probability that S minus its expectation, and expectation of the sum equals the sum of expectations. So it will be 1/2 times 16, which is 8. Which is E of S16. We need to divide by the variance of this variable, and this variance is going to be 16 times 1/12. And it should be greater than 12 minus 8 divided by the root of 16 over 12, which is the root of 4/3. Okay? So what we obtain then is that probability that S16 or just S is greater than 12 is approximately probability that standard normal variable Z. So we approximate this standardized variable by standard normal Z, although the accuracy of normal approximation is disputable here since the sample size 16 is not too large. But on the right-hand side, we have 12 minus 8, which is 4, divided by root of 4 over 3. So root of 4 is 2, so it will be 4 divided by 2 times root of 3. Okay. So therefore, it's going to be a probability that Z is greater than 2 times root of 3 or 1 minus capital Phi of 2 times root of 3. And how much would it be? Yeah, so we of course can use the table, but root of 3 is about 1.7. 2 times 1.7 is 3.4, which is greater than 3. By empirical rule, this probability is very close to 0. Therefore, we should get a number pretty close to 0. However, the accuracy of normal approximation is still an issue here. And our final question, 14, pertains to a multiple choice examination. So on this test, where we are just guessing from 4 possible answers, A, B, C, and D, we have 50 questions. And if a student answers completely at random, what are the chances of getting 15 or more correct? You may use the fact that a Bernoulli theta random variable has expectation theta and variance theta times 1 minus theta. So here we need to use the continuity correction, which I should address. So we approximate binomial distribution by the normal distribution using the de Moivre-Laplace theorem, but we really need to compensate for approximating discrete distribution, which is binomial, in terms of a continuous distribution, which is normal in our case. And this is achieved as follows. Okay. So here we deal with binomial experiment with n equal to 50 and probability of success in a single trial equal to 0.25, which is 1/4, so because it's sheer guessing here. And we need to find probability that it's greater than or equal to 15. So, but continuity correction basically states that Bn theta is between n1 and n2. So this probability is approximately probability that normal variable with mean n theta and variance n times theta times 1 minus theta will be between n2 plus 1/2 and n1 minus 1/2. And then we use standardization, which is probability that z is between n1 minus 1/2 minus n theta over the root of n theta times 1 minus theta. And on the right-hand side, we have n2 plus 1/2 minus n theta divided by the same thing, the root of n times theta times 1 minus theta. So adding up these guys, so adding 1/2 on the right and subtracting 1/2 on the left is the price that we have to pay for approximating discrete distribution with a continuous one. So if you don't subtract 1/2 here or add 1/2 over there, we still get a decent approximation. However, it's not going to be that accurate as we actually do employ this continuity correction. So this 1/2, actually, that's what is called the continuity correction here. Yeah. And this continuity correction is for de Moivre Laplace theorem only. Okay, and what actually frequently happens is that if this guy is actually added up here, so our n2 is 50 because it's not present here. We only have the lower bound. We can always put that it's less than or equal to 50, but when we do it, we eventually get a number outside 3 standard deviations range. Hence, our probability that b of 50 and 0.25 is greater than or equal to 15 is approximately probability that normal with 50 times 1/4 and 50 times 1/4 times 3/4 is between 50.5 and 14.5, which is in 1 minus 1/2. But really, this artificial upper bound is not going to be substantial because it will produce the numbers usually outside 3 standard deviation range. So, and this will be approximately probability that standard normal variable z is greater than or equal to 14.5 minus 50 times 1 quarter, which is 12.5 divided by 50 times 3 divided by 16, which is 50 times 3 over 16. So we have this root, and this is going to be probability that z is greater than 2. Then what we have here, like 50 over 16 is 25 by 4, so it will be 25 times 3 over 8. Yeah. So then we need to take the root of 8, and 8 will go to numerator. So it will be 2 times root of 2. And in the denominator, we will also have root of 25, which is 5 times root of 3. So, and therefore, what we need to find is probability that z is greater than 4 times root of 2 over 5 times root of 3, which is approximately probability that z is greater than 0.653. And this probability is about almost 26%, namely it's about 0.2578. So hence our probability is just slightly less than 26%. I thank you for your attention, and the course is over, and I wish you good luck on your final examination.